So in this video I want to talk through how to answer the questions that we didn't quite get enough time to go through in the GCSE Masterclass. They are questions 22.1, 23.3, 23.4 and 23.10. Now 22.1 is asking about current, charge and time. And in this question we are asked to calculate the time it takes for a certain amount of charge to flow. And so if I get my pen, our equation for current, the definition of current, is the amount of charge that flows divided by the time. Therefore, the time it takes for the charge to flow is going to be the total charge that flows divided by the current. So I've divided through by I and multiplied through by T. And if we substitute our numbers in, we get 360 coulombs of charge divided by 3.00 amperes of current, and that's 120 seconds, or 2 minutes. Now the second part of that question was asking how many electrons flow in that amount of time. Okay, so we need an equation here that is not given to you, an equation that you have to conjure up from your own mind. And that is that the number of electrons that flow the charge of each electron is equal to the total charge that flows divided by the number of electrons that flow. So this is the charge on each electron. Another way of writing this might be that the total charge is the charge on one electron multiplied by the number of electrons. Of course, we're interested in the number of electrons. So if we divide that second equation through by E, the charge on the electron, we get this. And that is the total charge that flows divided by the charge per electron is the number of electrons. And that's 360 coulombs divided by, and we use three significant figures, 1.60 times 10 to the negative 19 coulombs per electron. And that gives us 2.25 times 10 to the 21 electrons. And you can try and enter that into Isaac physics by just counting the zeros. I think I lost count whilst doing so. Just use standard form for that one. So that's 22.1. Now let's move on to the next one, which was 23.3. 23.3 looks a little bit like this. So I can doodle on this diagram now to show you how to solve 23.3. We're after these three potential differences. And what do we know? Well, let's follow our circuit. We trundle along like this and we pick up 4.5 volts. And then our charge goes through this resistor. And we don't know how many volts we drop off in that resistor. We carry on like this, then we get a choice. Let's go the top way because we've got numbers on the top way. So we drop off 1.1 volts. So we carry on. We drop off 1.5 volts. Then we carry on. Then we've got a choice. We can go the top way or the bottom way. Let's go the top way because we've got numbers on the top way. So we drop off 1 volt and then we drop off 0.5 volts. And then we carry on back on our way back to the power supply. And so according to Kirchhoff's second law, whatever potential difference we gain, that's 4.5 volts, across the power supply should be the same as what we drop across those resistors. So we drop V1, we also drop 1.1, 1.5, 1.0 and 0.5. That's me just reading those values clockwise, which is the direction the charge is flowing. So V1 is therefore going to equal 4.5 minus 1.1 minus 1.5 minus 1.0 minus 0.5. If I just look at my answers, that saves the day. I've already worked these out. That gives me 0.4 volts. See that? I'll have to write that underneath. 0.4 volts. Okay, so what about V2 and V3? Well, V2 and V3 are actually a little bit more straightforward. We don't have to worry about the rest of the circuit. So let's have a look at V2 to start with. On V2, the charge, and I'll use blue here, which will go green when I overwrite the yellow, but I think you understand what I'm trying to draw. The charge goes one of two ways. It either goes the top way or it goes the bottom way. If it goes the top way, we drop off 1.5 plus 1.1. That's 2.6 volts. So how much do we drop off if we go the bottom way? The same, 2.6 volts. And we could do the same thing on the second one. These two resistors added together produce a potential difference of 1.5 volts. And so V3 is also 1.5 volts. The components are in parallel, so the potential difference dropped across them is the same. Let's move on to the second one. So if this one, the first one of these circuits problems, was Kirchhoff's second law, the first one of these problems, the second one of these problems, is Kirchhoff's first law. Here it is. And I might make this a little bit larger so I can doodle on it. There we go. So on this circuit, you can see that we have 825 milliamps here in the circuit. So what do we have going through the first ammeter? 825 milliamps. It's right there. 825 milliamps. Then that current continues and arrives at a junction. Now if it goes the bottom way, then there's 37.5 milliamps. So what's left to go the top way, which is going through A2? Well, that's whatever was left. We had 825 milliamps. We tapped off 37.5 milliamps. And so what we're left with, I'll just read my answers to save me the embarrassment of trying to work it out in my head, is 700, I got it wrong anyway, 787.5 milliamps. And you wouldn't enter that into Isaac Physics. You could. It's clever enough to realise that that's correct, but it's far too many significant figures. So you're going to be giving this to about 788 milliamps. So then what do we do? Well, then we do the second junction. So here I've got my 788 milliamps or thereabouts, 788 milliamps. That 788 milliamps comes along like this, and then if it goes the bottom way, well, I don't know. That's what I need to work out. And if it goes the top way, well, I've tapped off there 37.5 milliamps. Remember, we're using the numbers that aren't in the square brackets. They're the more recent ones. The ones that are on the most recent books. And so we've got 788, I'm going to say 787.5. I'm going to use the unrounded number from the previous calculation in the next one, so I don't have an accumulation of rounding errors. And I'm going to subtract 37.5 milliamps, that's what we tapped off, and that leaves me with 750 milliamps. And that's the answer to A3. This is A2. And A1 is 825 milliamps. So that's Kirchhoff's first law. We already looked at Kirchhoff's second law in the first example. So now let's have a look at both of them together. And so in this question, this is question 23.10. We're asked for some voltages. We're also asked for some currents. So there's a lot going on in this question. So let's just fill in the answers that we can do easily first of all. And I'll use blue for the currents here because that's how they're already labelled on this diagram. So if I have 0.6 amps here and there's no junctions between that measurement of current and A3, then A3 is also 0.6 amps. Nothing's been tapped off. And so this is the current passing through here. And then if we look here, there's a junction, which I'll label with this splodge on the left. We've got 0.3 amps coming out at the bottom of that junction. And of course, 0.6 amps going in the top, because that's what we had on this wire here. So what is 0.6? This is for A1. 0.6 less 0.3. That's going to be 0.3 amps. And so this A1 is 0.3 amps. At this junction here, which I've drawn with a splodge, we've got 0.3 amps and 0.3 amps going in. And so this bit in the middle is back to 0.6 amps. We haven't used up any charge, so we haven't used up any current. It's all there. And then we have a junction indicated by this splodge there, the third splodge from the left, or the splodge on the right. And we have 0.6 amperes going in, and we lose 0.4 amperes along the bottom route. So what goes through the top route? 0.2 amperes. And that's all of the currents calculated. We now move on to the voltages, or potential differences, and I'll use red for this. So for the potential differences, we know that if we take the top route, let's use a pink colour, we pick up 9 volts, then we drop off 2 volts, then we drop off 3 volts, then we drop off 1 volt, then what have we got left to drop off here? So let's work that out. So for V3, we have 9.0 minus 2 minus 3 minus 1 equals 3 volts. So we drop off 3 volts at V3. Let's do V1 next. So if we went the top route, then we dropped off 0.3 volts on the resistor I've circled in red. Let's get rid of that pink so it's a little bit easier to see. So what have I dropped off if I take the bottom route? Well, it has to be exactly the same amount. So this is going to be 3.0 volts. And in fact, we can do exactly the same thing on the right. The resistor at the top drops off 1 volt. So what do we drop off if we go the bottom way? It has to be 1 volt. So V2 has to equal 1.0 volts. And that's all of the unknowns filled in for this diagram. Now there was one more question that I mentioned that I thought was worth going through. And that was, I think, the trickier question. It was on characteristics, which in your book is chapter 25. And it was question 25. Sorry, it wasn't on characteristics. My apologies. It was on resistance. It was on resistance, and it was question 24.9. Now, question 24.9 starts okay. You've got 2 graphs, which I've pasted here. And the first part, 24.9a, says, what is the resistance of the resistor when it is connected to a 6 volt power supply? Okay, so let's look at the resistor. That's the graph on the left. And on the graph on the left, we can see that we have, let's just turn my page to the right page. Question. Okay, 6 volt power supply. So we have 6 volts. I'm going to get a little straight line tool so I can clearly draw on this diagram. Let's try this. So it's 6 volts. Oh, hello, it's a big splodge. That's okay. So 6 volt power supply. We read it across. We read it up, sorry, then we read it across, and we convince ourselves that that is 0.3 amperes. And so this is for part A. We're asked for the resistance. We know that resistance is going to be equal to the potential difference divided by the current, which is 6 divided by 0.3. And you can use your calculator if you need to, or if you're pretty sophisticated at maths, you can work it out yourself. I'll use a calculator. That's 20 ohms. And then we move on to question B. So on question B, it says, what is the resistance of the resistor when carrying 0.2 amperes? Okay, so we need to clear off the lines we've got there. I'm only using the lines to show you what I'm looking at. And let's do that again with 0.2 amperes. So we read the other way on our graph. And we get 4 volts. Now, hopefully you see this is going to be a little bit of a pointless step, but I'll do it anyway. So 4 volts divided by 0.2, and my word, look at that. It's the same thing. Well, it should be. It's an ohmic conductor. That's what a fixed resistor is. So I'm quite reassured that it's the same number. It's supposed to be. Okay, so now let's move on to the next part, which is part C. And on part C, it says, what current would you expect to flow through the resistor if the voltage across it were 10 volts? Okay, well, it's an ohmic conductor. We've decided that already, which means we can say V equals IR. Let's get rid of that. V equals IR. We're asked what the current would be expected, so that's I is going to equal V over R. If we have 10 volts divided by its 20 ohms, because it's an ohmic conductor, we've worked it out once, we've worked it out twice, it's not changed. And so that's going to be 0.5 amperes, 0.50 amperes. Okay, now D. Part D, again, it's not so bad, part D. This time we're looking at the lamp. So for part D, it says, what is the resistance of the lamp when it's connected to a 4-volt power supply? So we get our colourful pen, 4-volt power supply, read it up, read it across. We know that our resistance is going to be the voltage divided by the current. The voltage is 4, the current is 0.5, and that gives us, let's just look at my working to make sure I've not done something daft. Yes, 8. Why on earth did I check that? 8 ohms. Okay, so part E then. So part E is wired resistor. Sorry, you wired the resistor and the lamp in parallel and connected them to a 6-volt supply. I think we need a diagram, don't we? I'm just going to make a note on this diagram that this is 20 ohms because I'm fairly sure that information is going to be useful later. Let's delete these lines. I don't want them. Let's delete these lines. I don't want them. And let's give myself some working space by removing all of my working from before. Okay, so let's draw a little diagram. You might not need to draw a diagram, but I encourage you to do it anyway because it's good practice. So always draw a sketch when you're unsure. All physicists do it. Okay, so we've got our fixed resistor. We know that's 20 ohms. That's fine. And we've got our lamp of some unknown resistance. It seems to be changing. And it says that we wire these across 6 volts. So this is 6 volts from here to here. And it says how much current would be taken in total from the supply. So in other words, let's stick an ammeter in series with this network and see what goes through it. Okay. Well, if it's 6 volts across the top resistor, so we pick up 6 volts, we drop them all off, and that's all we've got, we can work out the current. 6 volts, 0.3 amperes. So I know that I've got 0.3 amperes in that top branch. But what about the bottom branch? Well, the potential difference across the bottom resistor, which isn't a resistor, it's a lamp, the potential difference across the bottom lamp is also 6 volts because they're in parallel. Kirchhoff's second law. So that means I have a current of 0.6 amperes. And so what has to flow through the remainder of the circuit? 0.9 amperes. Okay, so, or 0.90 amperes. Let's not be lazy. So then we move on to F, which is ominously labelled as harder. And the reason why it's harder is because if you look at the question, it says we're now using a 14-volt supply. And yet if you look at both graphs, you'll notice that the resistor goes up to 6 volts and the lamp goes up to 6 volts. And we're wiring these in series. So let's draw a sketch. fixed resistor, filament lamp, and we're going to put 14 volts across it. I'll indicate that with a power supply. 14 volts across this mess. 14 volts. I hope you can read that text. Okay, so who gets what share? That's the problem. Because if this gets 6 volts and this gets 6 volts, that's only 12 volts, which isn't enough. But if any one of them gets more than 6 volts, then we've gone off the end of the graph. Oh no. So how are we going to get our data? Well, fortunately, we can extrapolate this fixed resistor graph. Because it is a fixed resistor, so the resistance isn't changing, we know that as this goes through the origin, this relationship goes through the origin, we're going to get a perfectly straight line all the way up. Which means that we can predict at any voltage what the current would be through it. We can't do that with the lamp. So let's start guessing. Let's start guessing. It's the only way we're going to be able to do this. What if we had 6 volts across the lamp? If we had 6 volts across the lamp, that means we would have to have 8 volts across the fixed resistor. We know that the current through each must be the same. So that means that we're saying the current through the lamp must be 0.60 amperes. So is that going to be the current through the fixed resistor? You take your calculator out, you work out what the current is based on 20 ohms and 8 volts. So I equals V over R. You plug in 8 over 20. It doesn't look promising. So 8 over 20 is 0.4 amperes. It doesn't agree. The current is vanished. What does that tell us? That proposed solution is wrong. So what else can we do? Well, I suppose we can reduce the voltage on the lamp. So let's try a different one. And I'm quite a lazy individual. I don't want to have to interpolate. So I'm just going to try 4 volts. Let's try 4 volts there. So that gives me a current of 0.5 amperes. And I don't have anything on my graph, because my resistor graph, because it goes off the scale. But if this one has 4 volts, so that's 0.5 amperes, then this one here has to have 10 volts. Now, if I had 10 volts, what would the current be through it? That would be equal to the potential difference divided by the resistance. Potential difference across that is 10 volts, and the resistance is 20. Huzzah! That sounds a lot like 0.5 amperes to me. So that agrees. They've both got the same current, which is Kirchhoff's first law, because the potential difference is shared between the two components in a loop. That's Kirchhoff's second law. So what was the question? It was what would the current be? 0.5 amperes. And what would be the voltage across the lamp? 4 volts. And that's how you find the answer to that much harder question. A small amount of trial and error, but when you get to A level, we might teach you how to work it out in a more analytical way. Thank you very much.